Hey everyone, on March 18th, I blood tested for the second time in 2026. And note that this is test number 67 since 2015. So with that in mind, what's my biological age? That's what we'll see here. This is using Dr. Morgan Levine's biological age calculator, PhenoAge. And if you want to measure this test yourself, I have a new custom blood test panel on ultalabtest.com. And if you're into blood testing like me and you want to help support the channel and calculate your biological age, you can do that by using the affiliate link in the video's description. Additionally, if you're watching this on YouTube, note that these data were posted on Patreon almost 2 months ago. So if you want to see the data as soon as it comes out, almost immediately after I blood test, check us out over on Patreon. All right, so when entering these 9 biomarkers and chronological age, I get a biological age of 35 years, which is 18.1 years younger than my chronological. The maximum reduction for chronological age minus biological age using this test is close to 22 years, which I've achieved once. So 18 years, not too bad for this test. In terms of where can I improve, it's the MCV, which has remained relatively high for several tests going back to 2025. Now, I've tried various interventions in following correlations within my own data over that time span with no luck so far. And I've detailed that in other videos. I won't go through the MCV story again in this video, but stay tuned for the update for when I'm able to reduce it in future videos. But note that this is just one test, and I see a lot of people talking about their biological age online these days, taking maybe 1 or 2 tests per year. But is that a true biological age if you're only measuring once per year? Ideally, we should have test data every day to get a full 365-day average for biological age, or for any biomarker really. Now, with that in mind, I'm testing a lot more often, because I think that in testing more often and taking the average of all of those tests in a given year, and then taking year-to-year average and tracking that over time, that's a true pace of aging. So with that in mind, for more context, let's take a look at year-to-year change, as I have 47 test results for PhenoAge going back to 2018, which is what we'll see here. So again, this is year-to-year change for biological age using Dr. Morgan Levine's test, PhenoAge. Now, when I first started measuring in 2018 to 2019, I wasn't including hsCRP at every test because this biological age test hadn't yet been published, and at that point, I didn't understand the importance of hsCRP. But starting in 2018, I started to include it for every blood test going forward. From 2018 to 2019, I only had 3 tests with an average biological age of 34.3 years. So then in 2019 to 2020, I started testing more often, 6 tests each in 2020 and 2021, with an average biological age in each of those years exactly 33.9 years. Although the 3 tests over a 2-year span in 2018 to 2019 was 34.3 years, that might have actually been close to, or a close representation to where my data actually was, because when I measured more often, 12 times over the next 2 years, we can see that it was pretty close to 34 years. Now, that may be a statistical anomaly, because for most people, I'd say the variability may be much greater. Maybe you test once and it's 34. Maybe you test again and it's 42. And if you're only measuring once or twice per year, what is the actual data? Is it 34? Is it 42? So in testing a lot over a given period of time, for example, in a year, we can take that average and then track year-to-year change, which is what we've got going on here. In 7 tests, I then increased the testing frequency in 2022. Average biological age was 32.1 years, and this is my best data yet, as we'll see, over the approximately 8-year span. Over another 7 tests in 2023, average biological age using this test was 32.9 years, moved a bit in the wrong direction. And then I increased the testing frequency in 2024 to 8 tests, and I'm going to stay at 8 tests per year. I think once every around 6 weeks is a good duration in between tests, so I'm going to stick with 8 tests per year going forward. So in 8 tests in 2024, average biological age using this test was a bit higher, 33.1 years. And then it got even worse in 2025. Over 8 tests, back to essentially where I started in 2018 to 2019 with an average of 34.2 years. I wish I could say that I've flipped it and gotten it back to 32.1 years in 2026. Not so much. So after the first 2 tests in 2026, so January and March tests, average biological age is 35.4 years. So as I mentioned, this is a true pace of aging, not 1 or 2 tests over a given 1 or 2 year period. This is 47 tests over an 8+ year period. To evaluate that pace of aging, we can see that it's basically pretty close to flat. I mean, if I didn't have the 35.4 years over these first 2 tests, I'm basically where I started 8 years later with essentially no change for the 9 biomarkers that are contained within this test, which would be good news. But to keep it fair and balanced, we can see that the data has been moving in the wrong direction for a few years, starting in 2022. So I've got to reverse that MCV increase that I've seen over the past few tests in order to get my data back down to around 33 relative to 35. But note that I'm measuring a lot more than these 9 biomarkers, as quantifying biological age using this test is only a small part of my overall approach, with the goal of optimizing biomarkers of as many organ systems as possible. I often get asked, in terms of testing hierarchy, if you could narrow down blood tests to a particular few, what should people measure? Cardiovascular disease is the top cause of death worldwide, and I've got CVD in my family. My dad's brother died at 51 after having a stroke at 47. My dad's father was dead at 67 from cardiovascular disease. And on my mom's side, my maternal grandfather died at 67. Now, granted, he drank a lot of alcohol, so that probably wasn't CVD related, but longevity is not in my family. So if I'm going to get to my stated goal of living longer than anyone that's ever lived, I've got to literally science the out of aging in order to do it. Atop that list are CVD-related biomarkers. For that, I'm going to show data for risk-weighted ApoB. And if you missed the importance of not just tracking ApoB, but risk-weighted ApoB, I'll link to that video in the right corner. The risk-weighted ApoB metric includes ApoB, lipoprotein A, and triglycerides. And note that I'm not going to my doctor to measure these tests. I order exactly the tests that I want, including these that are shown here, and a lot of other ones, as I'll go through later. I then bring that test form to Quest Labs, who draws the blood for about a $10 blood draw fee, and then I get the results relatively quickly. You can see that I measured it at around 7 in the morning on March 18th, and then all of the results were in 8 days later. TNF-alpha took the longest to arrive. Note that most of these results were in 1 or 2 days after testing. If you're into blood testing like me, and you want to help support the channel, you can do that by using the affiliate link in the video's description. All right, what was the data? ApoB was 67, which then raises another question of what's optimal for ApoB. To address what's optimal, I have a new Patreon tier dedicated specifically to what's optimal for biomarkers, which includes data for ApoB, but also for 36 other biomarkers, 62 published references, 2.5 hours of video content. And note that these aren't just the reference ranges, which you can get from any LLM these days. In fact, if you put all of the biomarkers on this list into your favorite LLM and ask it to give you quote-unquote optimal ranges, well, first it'll probably give you the reference range. But if you ask it to give you the optimal ranges based on how each of these biomarkers changes during aging and their associations with all-cause mortality risk, in the largest studies that exist for each of these biomarkers, it'll give you a pretty good list. But the devil's in the details. And on this tier, I go through the actual data. This isn't just a list of biomarkers and what's their optimal ranges on a piece of paper. This is the actual plots from all of those papers in one spot. Can't get that from an LLM. LLM will just give you the generic, this is the range. So if you want to dive deep into what's optimal for biomarkers, check us out over there on Patreon. In giving away that story, my what's optimal target is less than 70 milligrams per deciliter for ApoB, as that's significantly associated with lowest risk of death for CVD-related outcomes, but also all-cause mortality risk. So for that, 67 is less than 70, so we give it a green check. Good news. For lipoprotein A, though, not so good news. And if you've followed me for a while on the channel, you know that almost all of my lipoprotein A data is either just outside of the reference range or towards the higher end of the reference range. And you can see that the lab flagged it at 88 nanomolar, which is high relative to their upper limit of the reference range, which is 75 nanomolar. Now, for those who don't know, lipoprotein A is 6 to 7 times more atherogenic than LDL. So for a given LDL particle and a given lipoprotein A particle, lipoprotein A would be 6 to 7 times more atherogenic than LDL. And if you missed that video, I'll link to it in the right corner. So this is potentially bad news, the lipoprotein A data, but I'll have more on that in a minute, why it may not be as bad as it seems just superficially. Triglycerides for this test were 54 milligrams per deciliter. My what's optimal target is less than 45, as that's significantly associated with lowest risk of death from CHD, coronary heart disease related outcomes. And that too is on the what's optimal tier. So 54, not too far away from 45, but just a bit outside of optimal. With these 3 pieces of data, now I can calculate risk-weighted ApoB, which accounts for the atherogenicity, the greater atherogenicity of lipoprotein A and triglycerides relative to LDL. And when entering these data, I get a risk-weighted ApoB that's higher than my ApoB of 75 milligrams per deciliter, just now outside of the what's optimal. So let's dive a little bit deeper into the lipoprotein A story. Lipoprotein A associated atherosclerotic cardiovascular disease, ASCVD risk, is lower when hsCRP is less than 2 milligrams per liter. And if you missed that video, you got a lot of videos to watch. I'll link to that in the right corner. So what's my hsCRP data? For those who already paid attention to the opening biomarker data on the first screen, biological age data, it included hsCRP. And there we saw that it was 0.2 milligrams per liter. The actual test value that I got on the test report is shown there, which is less than 0.2 milligrams per liter. So at its highest, it's at the lab detection limit of 0.2 milligrams per liter. So it could be lower, but not higher than 0.2 milligrams per liter. This is potentially good news. Lipoprotein A associated ASCVD risk is highest or higher when hsCRP is greater than 2, not 0.2 milligrams per liter. So my data is actually 10 times lower than this cut point for lipoprotein A being significantly associated with ASCVD related outcomes. So this is good news. Relatively high lipoprotein A, but super low hsCRP. And this isn't an anomalous test. For the 14th test in a row, hsCRP is now at that detection limit or lower, 0.2 milligrams per liter. For Quest, note that their detection limit once upon a time was 0.3 milligrams per liter, not 0.2 milligrams per liter, which has been a recent improvement for their testing. Going back 30 tests, it's now 30 tests in a row where hsCRP is less than the lab's detection limit of 0.3 milligrams per liter. Now, I'm generally not competitive when it comes to biomarkers with other people because my competition is against myself and with aging. But I'd be curious to see if anybody has a streak this long, hsCRP lower than the lab's detection limit, at most 0.3 milligrams per liter. As far as I know, I think this is the longest streak of anyone, maybe on Earth. All right, but I'm not just only tracking these biomarkers, risk-weighted ApoB, to evaluate cardiovascular disease risk. I'm also tracking biomarkers of the omega-3 index, as that's a biomarker of CVD risk. And we can see why that's the case in studies like this that looked at relative risk for sudden cardiac death by risk factor. So on the y-axis, we've got RR-SCD, so relative risk for sudden cardiac death. And then that's plotted in a head-to-head matchup of many different biomarkers, including CRP, homocysteine, HCY, TC, total cholesterol, LDL, HDL, triglycerides, the total cholesterol to HDL ratio, and the omega-3 index, N-3 index. And on this list, we can see that only 2 of these biomarkers are significantly associated with sudden cardiac death. CRP, so when CRP is high, in this study, it was significantly associated with the highest risk of sudden cardiac death. And conversely, when CRP was at its lowest, that was associated with about a 60% lower risk of sudden cardiac death relative to people who had a high hsCRP. Additionally, we can also see that the omega-3 index was also associated with risk of sudden cardiac death. So for people who had the lowest omega-3 index, that was associated with the highest risk for having death by heart attack, or immediate death by heart attack, or sudden cardiac death. On the other hand, people who had the highest omega-3 index had significantly reduced risk of death from sudden cardiac death. In fact, if we look at the highest omega-3 index, that was associated with a 90% reduction for sudden cardiac death relative to people who had the lowest omega-3 index. So we can see that in a head-to-head matchup versus lipoproteins and homocysteine, CRP and the omega-3 index may be a better metric, at least for looking at sudden cardiac death. But let's take a sidestep. What exactly is the omega-3 index? It's the proportion of omega-3 fatty acids, EPA and DHA, which most of us think of as found in fish oil and fatty fish, EPA and DHA that are found in red blood cell membranes, which then raises the question of what's optimal for the omega-3 index. And don't worry, you don't have to go to Patreon to get that data. I'm going to show it here. For high risk for the omega-3 index, that's associated with sudden cardiac death, but also risk of death from coronary heart disease and death for all causes. And that's associated with an omega-3 index that's lower than 4%. Conversely, when the omega-3 index is higher than 8%, that's associated with lowest risk for these 3 outcomes: sudden cardiac death, coronary heart disease, and death from all causes. Which then raises the question of what's my data? To address that, I'm using at-home metabolomics, as this kit, Iolo's at-home metabolomics kit, includes 2 metabolites, these 2 PCs, phosphatidylcholines, 36,5 and 38,6, that are significantly associated or strongly associated, as we'll see in a second, with the omega-3 index. And the reason that I'm using this kit instead of just tracking the omega-3 index directly is because this kit includes more than 600 other metabolites. So I'm getting maximal bang for my buck relative only to only paying for the omega-3 index, I can look at biomarkers of the omega-3 index, these 2-phosphatidylcholine, and get data for 600 other metabolites, many of which I've covered on the channel. So if you want to test these metabolites yourself, discount link in the video's description. Let's take a look at the data about how these two metabolites, these 2-phosphatidylcholine, are strongly associated with the omega-3 index, which is what we'll see here. On the x-axis, we've got the omega-3 index, and on the y-axis, we've got the sum of these 2-phosphatidylcholine. And I should mention, for those who haven't seen that video yet, these 2-phosphatidylcholine contain EPA and DHA. So it shouldn't be a surprise that they're strongly, as we'll see in a second, that they're strongly associated with the omega-3 index, which is what we'll see here. And in terms of the correlation, you can see that the correlation coefficient is 0.766. Anything greater than 0.7 is considered a strong correlation. The sum of these 2-phosphatidylcholine are strongly associated with the omega-3 index. So in terms of what's optimal, we can then put up a green line at that 8% cutoff. And then based on extrapolation of the trend line, we can see that when the sum of these 2-phosphatidylcholine is greater than 60 micromolar, that's significantly associated with an omega-3 index that's at least 8%, which, as we just saw, was associated with lower risk for sudden cardiac death, lower risk for having coronary heart disease, and lower risk for death for all causes. All right, so what's my data? Because as I mentioned, the goal is to optimize CVD-related biomarkers. That's what we'll see here. This is the sum of these two omega-3 index associated metabolites, as I have 24 tests going back to 2023. When I first started measuring over 5 tests in 2023, it was greater than that 60 micromolar cutoff at 93 micromolar. But then note that over the past 3+ years, the data has moved in the wrong direction. Over 9 tests in 2024, average was 91 micromolar. Over 8 tests in 2025, 76 micromolar. And after the first 2 tests in 2026, 62 micromolar. In terms of the what's optimal target, the average of all of these data is greater than 60 micromolar. So that's good news. But we want to also resist age-related change. This isn't just about having data in a quote-unquote optimal range. It's looking deeper into the details. And those details are, we can clearly see that the data has moved in the wrong direction. And if I don't pay attention to trying to improve it, well, maybe it's going to get even worse. That then raises the question of, how can I resist the age-related decline for the omega-3 index? And to do that, let's take a look at correlations for diet with these two biomarkers that are strongly associated with the omega-3 index. To get there, we've got to first take a look at how I'm able to even do that. The approach of calculating correlations for diet and supplements with biomarkers. Since 2015, I've weighed literally all my food using the food scale there. And that's a stock photo. I didn't put a singular almond on the scale. So that's just a stock photo. I almost never eat out. And granted, I get it. Some people can't do that or think that I'm a crazy person for doing that. I enjoy it. I enjoy treating my body as a chemistry experiment, a biochemistry experiment. More than 99% of all data since 2015 has been weighed. I then enter that data into a diet tracking app, Chronometer, and if you want to track your own diet using Chronometer, there's a discount link in the video's description. I then take the Chronometer data and export it into a spreadsheet, including macro and micronutrients, but also individual foods. So macros and micros are good, but that's kind of a reductionist approach relative to the foods themselves. So it wasn't until 2018 when I had the idea I should start tracking actual food intake and not just macros and micros. So I enter all of that data into a spreadsheet, and then each blood test has a corresponding average dietary intake. In other words, if there are 50 days in between blood tests, for that 50-day period, if I take the average, I can then line it up with the latter blood test. So now every blood test has a corresponding average dietary intake. And then once you get to 3 blood tests, you can start looking at correlations. Now you could say 3 blood tests, looking at correlations, there's a lot of noise relative to the signal. And this is true. But this is the beginning of the journey to start to separate the signal from the noise, because those 3 tests will start to give you insight into what you can do to try to move biomarkers in the right direction relative to wrong. And then after 4 tests, and then after 5 tests, it's the F around find out approach, where you use data to guide decisions and then you recalibrate after each test by calculating the correlations again. Now note that technically you could use 2 tests. You can look at differences between 2 different dietary periods, so 50 days before test 1, 50 days before test number 2, and use a 2-sample t-test to see what might have been different in between tests. So you don't even have to wait to get to 3 tests to start using data and the statistics to try to guide decisions in terms of what may move biomarkers in the right direction versus wrong. All right, so now we can get back to this original question of what's significantly correlated with a higher omega-3 index or biomarkers of the omega-3 index in my data. And the first obvious place to start would be fatty fish, right? Because fatty fish contains EPA and DHA. So since 2015, I've almost exclusively consumed sardines as my source of fatty fish. Salmon has been in the approach occasionally, but I've basically eaten sardines every day for the past 10 plus years, 11 plus years. Let's take a look at the plot for sardines versus the sum. That sigma sign is a sum of the two metabolites that are strongly associated with the omega-3 index, which is what we'll see here. On the y-axis, we've got the sum of those two metabolites plotted against the average daily sardine intake. And again, the average daily sardine intake that corresponds to each blood test. Each data point is an average daily sardine intake that corresponded to that test. And although the correlation is positive, which suggests that higher sardines may impact higher levels of these two metabolites that are biomarkers of the omega-3 index, that p-value is nowhere near statistical significance, as the p-value is 0.62. And that correlation of 0.11 is very weak. As we'll see, I'm going to show plots for three other variables, three other foods and or nutrients that have stronger correlations with these two biomarkers of the omega-3 index. With that in mind, what about other sources of EPA and DHA? In my case, it looks like, for whatever reason, sardines may not be the driving factor to increase levels of these biomarkers that are strongly associated with the omega-3 index. So let's take a look at flax seeds versus the sum of these two metabolites. Flax seeds contain omega-3 that can be converted into EPA and DHA. And then, if EPA and DHA are freely floating in plasma, they can be incorporated into red blood cell membranes and correspondingly a higher omega-3 index. But the argument against that is that there are published papers showing the conversion of omega-3 fatty acids found in plant-derived sources, in flax seeds and walnuts and other foods like chia. It's a relatively inefficient process, or at least that's what the publications have shown. It was pretty surprising to me, though, to see that flax seeds are actually close to statistical significance for a higher level of the sum of these two fatty acids that are strongly associated with the omega-3 index. As we can see that the correlation coefficient is stronger, 0.36 relative to sardines, but that p-value is just outside of statistical significance at 0.09. If we only rely on the stats to guide decisions, this too may be a faulty approach. Because although these are correlations, and I don't presume to claim causation, but I can get close to testing causation by testing the correlation. If this is a real correlation, if I increase intake of flax seeds to greater than my highest levels on this chart, 30 or 35 grams per day, what will happen to this correlation? If the correlation continues on that upward trajectory, in other words, going even higher for flax seeds may lead to an increase for levels of these two metabolites that are strongly associated with the omega-3 index, that would suggest this is a real effect. But if I increase flax seeds to say 35 grams per day, and the sum of these two fatty acids is say 40 micromolar, well, that would suggest it's not a real correlation, and that correlation coefficient will weaken, and the p-value will move farther away from 0.05. That's the plan, part of the plan for the next test, to increase flax seeds 30 to 35 grams per day on average to test this correlation. What about walnuts? Because walnuts also contain omega-3 that can be converted into EPA and DHA. And I should also say, if I focused on only the published literature, studies and others, or in vitro studies, I would never see the actual data within myself. I mean, it's pretty much a surprise that flax seeds may be driving some of the effect for higher levels of biomarkers that are strongly associated with the omega-3 index. If I only focused on those published studies, I wouldn't ever think to do that experiment. So it highlights the drive of personalization to really get after what may be the story in your own data relative to studies and others. On to the walnut data, which is actually the opposite of what we see for flax seeds. Now we can see a close to significant inverse correlation, negative 0.38, which suggests that higher walnuts is correlated with lower levels of these metabolites that are strongly associated with the omega-3 index. But here too, note that p-value is just above the threshold for statistical significance at 0.07. Now, I'm not going to test the walnut correlation by either reducing it to close to zero or going higher than where I currently am at 35 grams per day, because in my data, for whatever reason, homocysteine seems to go higher with very high intakes of walnuts. So I've had walnut intakes that are close to 70, 80 grams per day on average, and those are actually my worst data for homocysteine, as high as 12 micromolar. Now, I don't know what the mechanism would be for too high of a walnut intake, if it's even causation, but I've noted that when walnuts are closer to the lower end of my range, for this test, it was about 35 grams per day. Homocysteine is about 10 to 11 micromolar relative to my highest, 12 micromolar. And I'm not trying to have homocysteine go even higher, and that's a story for another day. But these are relatively weak correlations, 0.11, 0.36, negative 0.38. Are there stronger correlations for diet with the sum of these two phosphatidylcholines that are strongly associated with the omega-3 index? And I should mention that I've started here, sardines, flax seeds, and walnuts, because they either contain EPA and DHA, or they contain the fatty acid precursors, omega-3, that can be converted into EPA and DHA and then correspondingly incorporated into red blood cell membranes. But there are actually other stronger correlations in my data, including beets and monounsaturated fatty acids, or MUFA. Note that these 4 correlations that I've shown, there are a lot more correlations, and not just with these 2 biomarkers of the omega-3 index. I post correlations for all data, including the standard chemistry panel, metabolomics, and everything else, sometimes even sleep. So if you're interested in that, check it out on the correlations tier on Patreon. So on to the data. First, starting off with beets, some of the 2 phosphatidylcholines that are strongly associated with the omega-3 index, and that's plotted against the average daily beet intake that corresponds to each test. And here now we can see a significant positive correlation with a correlation coefficient of 0.50, and that p-value is significant at less than 0.05. These data suggest that when beet intake is at the lower end of my range, or 0, that's significantly correlated with my lowest biomarkers of the omega-3 index. And conversely, when beet intake is highest, around 300 grams per day, that's significantly correlated with my highest biomarkers of the omega-3 index. But here too, it's just correlation. And to test causation, instead of keeping beets at the lower end of my range, which I've done for the past few tests to try to limit oxalate intake, for the next test, I've added beets back into the approach, at least 150 grams per day. I'll probably settle somewhere between 150 and 180 grams per day. Today was about 180 grams per day, which will test this correlation somewhere around the midpoint. If we extrapolate based on the trend line, I should see values closer to around 75 micromolar relative to around 60 micromolar with no beets, if this is a real correlation. If it's not a real correlation, adding beets back into the approach, this correlation will weaken and other stuff will pop up, and then I'll continue to follow the correlations until I discover the recipe for resisting the age-related decline for these 2 biomarkers of the omega-3 index. What about monounsaturated fatty acids, or MUFA? That's what we'll see here. Some of the 2 metabolites that are strongly associated with the omega-3 index on the y-axis, plotted against the average daily MUFA intake that corresponds to each blood test. And now these data are actually the opposite of what one might expect. We think about monounsaturated fatty acids, we think about heart healthy. Maybe not in my case, and it's not just for biomarkers of the omega-3 index. I also see a similar pattern for glucose levels with very high levels of monounsaturated fatty acids in my diet. And note that these aren't coming from olive oil, which has been an almost never in all oils in my approach, as I favor whole foods over the processed products. This is from whole food, from nuts, seeds, avocado. But again, this is just the correlation. So here we can see that the correlation is negative 0.57. It's the strongest correlation of the 4 correlations that I've shown in this video. And the p-value is significant at less than 0.05 at 0.004. Note that the data may be even worse for the test number 3, metabolomic test number 3, which I just sent off for the April 29th test. For that test, average MUFA intake was even higher than what's on this plot at 55 grams per day, as I was testing a significant correlation for monounsaturated fatty acids with lipoprotein A. If this is a real correlation, by going even higher for monounsaturated fatty acid intake, we'd expect to see that the sum of these 2 metabolites that are strongly associated with the omega-3 index may push it even lower. I'm not convinced that that's what I'll see. I think this correlation will weaken. It may be beets that are driving the story, but that's one way we can get to personalization, is by tracking our own data over a long period of time in conjunction with tracking diet, supplements, and a whole host of other variables. It didn't just track cardiovascular disease risk biomarkers and biomarkers of biological age. For the March 18th test, I tested a whole bunch of other stuff as shown here. So I showed data for ApoB in this test, some of the data on the chemistry panel and complete blood count that are included on the biological age test. I also showed some data for the lipoprotein A and triglycerides and hsCRP, but there's a lot more data that I didn't cover, all of which is covered on Patreon. So if you're interested in that, check it out. On the same day as this test, I also measured my oral microbiome, now for the 20th time, as I've had issues with this singular bacterium dominating my oral microbiome from the majority of those tests, at least 85% of all of the bacteria in my mouth being a singular bacterium, which is bad news. And I can already hear some people in the comments saying, well, maybe the test isn't great, maybe it's just noise. To see that singular bacterium, which is only found in 1 to 3% of all people who have used this test, in my case being the majority dominant oral microbe for a majority of tests, not good news. But without going over to Patreon, the good news is for the past 2 tests in a row, 0%, which has been a rare event relative to all the other tests. So I'm going to keep measuring my oral microbiome for every test. And if I've been able to eradicate that microbe and now have an actual normal oral microbiome, or quote unquote normal oral microbiome, then I'm going to start looking at correlations for oral microbes with diet, with the goal of minimizing periodontitis related oral microbes. So that's a story for another day. That's a developing story. So stay tuned for that data in an upcoming video. If you want to see all of the data that I've shown here, all of those results are on Patreon. And additionally, note that I offer blood test consults. So if you're interested in that, check it out. I also post at least twice per day in 4 other Patreon tiers. And we've also got a whole bunch of discount and affiliate links that you can use to test yourself that help support the channel, including ultralabtest.com, which I mentioned in the video, Life Extension, which has a whole bunch of other tests. They are using Quest now, and originally I included the Life Extension affiliate link because ultralabtest.com uses Quest. So I wanted to have an affiliate link for people who use LabCorp, but recently Life Extension switched over to Quest. So anyway, Life Extension actually has some tests that are cheaper, like CD4, CD8 is a cheaper test there relative to the ultralabtest.com. So if you're into blood testing and you want to help support the channel, I've got 2 affiliate links, Ulta and lifeextension.com. At-home Metabolomics, which I mentioned in the video, NAD testing with Ginfinity, which I tested more than 30 times to come to the conclusion that 500 milligrams of NMN per day gets my data to around 40 micromolar, which may be optimal in my case. Epigenetic testing with True Diagnostic, which includes Dunedin Paste, one of the best epigenetic clocks of epigenetic clocks. At-home blood testing with SciFox Health, which includes the best epigenetic clock of epigenetic clocks, GrimAge. Oral microbiome composition, which I just mentioned. Diet tracking with Chronometer. Green tea, which I'm back to drinking every day now that the tariffs are gone from Japanese imports. The clearly filtered water filter, which I use every day. Or if you'd like to support the channel, you can do that with the website, Buy Me a Coffee. We've also got merch, including Data is my North Star, Figuring Stuff Out is my drug, or the ConquerAging or Dietary logo, which I've got on here. Link in the video's description. Thanks for watching. I hope that you enjoyed the video. Have a great day.